Gonzalo Morales, and this is my Physics 2212 Lab 4 report, Circuits and Capacitors. The purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel. Use multimeters to measure the actual values of conventional current and potential differences in the circuits and examine the behavior of ohmic resistors and capacitors. Some of the fundamental principles that we'll use is the principle of energy conservation and current conservation. The equations I used were V equals IR, the loop rule where the total potential differences around the whole loop is equal to 0, and the node rule where N equals out for the current and then R times C is equal to seconds. In order to complete this lab, I had to download the circuit construction kit and follow the instructions included in order to conduct the lab experiment. The way I set up the circuit was by adding two circuits, two batteries, and the battery total voltage is 3. Based on the voltage formula, I predicted the voltage to be 0.0204 amps. So my prediction was correct based on the experiment. When you reverse the connection of one of the ammeters, it becomes negative 0.0204 amps. Next, we had to create an open circuit. The potential difference is negative 3 volts, because the first reading will be negative 3 volts. Then the second reading will be 0 volts, because no current flows through it. The ammeter reads 0 amps because no current is flowing through the wire. This is my graph of potential differences versus position. A would be where our battery is, which is 3 volts. Then it goes from B, the wire, which has 0 resistance, so it will be a constant. Then at C, it goes down by negative 0.96 because it finds our first resistor. Then we have another wire, so it is constant, and then another resistor, which makes it negative 0.204 volts. For the second part of the lab, we had to create an RC circuit. What I did first was charge up the capacitor and was able to see that when it is charging up, the current is moving to the capacitor and the capacitor gains charge. Then, when we take out the battery and the capacitor loses charge, causing the current to leave the capacitor into the light bulb. Next, we had an experiment of charging and discharging based on resistance. It took us 6.4 seconds to charge up the capacitor with 10 ohms and 6.4 seconds to discharge it. It also took us 12 seconds to charge up the capacitor with 20 ohms and 12 seconds to discharge. These results make sense since the resistance is twice as large and V equals IR. Then we had an experiment of finding RC, the time constant of the circuit. I did this by setting up the system with a 9-volt battery and a 0.2 for the capacitor, and I had a 30 ohm resistor. I used a stopwatch to time it and measure its voltage and its discharge within 20 seconds, and this is the result. I plotted time versus natural log of delta V over delta V initial graph, which would be 9, and we get this linear negative slope plot, and we get a negative slope of negative 1 over RC, and for my plot the slope was negative 0.1662. And then after doing some algebra, we get our RC value to be our 6.0168 seconds, which is very close to our expected value for RC, which was 30 ohms times 0.24 odds equal to 6 seconds. Next, we have the what if questions for the conclusion of the lab. First, we have what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter and how would it have affected the circuits you hooked it up to? Well, an ammeter is designed to have very low resistance, so an ideal ammeter has exactly 0 resistance. This is not possible in real life, as all objects have some level of electrical resistance, and even the best ammeters have a very small amount of resistance. Adding resistance to a series circuit decreases the amount of current flowing through it, so had we done this lab in real life, we would be getting lower than expected current values due to internal resistance of the ammeter. For the next question, we have what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Our ideal model would predict that the capacitor would be charged instantly. This is due to the fact that the model assumes no resistance in the wires or the battery, and therefore an infinitely large current would be able to flow and charge the capacitor instantly. In real life, there is always a little bit of resistance in the batteries and wires, so the capacitors cannot be charged instantly, although it would charge fairly quickly as predicted by our model. Thank you for watching.